Sometimes we can find the zeros or x-intercepts of a function by factoring, or maybe by using the quadratic formula. But sometimes we have to approximate. This video is about Newton's method for approximating zeros. Let f at c equal 0, in other words, c is a zero of the function, where f is differentiable on an open interval containing c. Then to approximate c, use these steps. Step 1, make an initial estimate x1 that is close to c. Step 2, determine a new approximation using this formula. Here's what the formula is really saying. You can get a new guess by taking your old guess and subtracting f at old divided by f prime at old. When the difference between the old guess and your new guess is within the desired accuracy, then your new guess will serve as your final approximation. Otherwise, repeat step 2. Each successive application of this procedure is called an iteration. If the values get closer and closer together, they are said to converge. So this will make more sense once you look at an example. Calculate 3 iterations of Newton's method to approximate a zero of f of x equals x squared minus 2. Use x1 equals 1 as the initial guess. For Newton's method, we need the first derivative. So the first derivative, using the power rule, I'm just going to get 2x. Don't forget, here's Newton's method right here. The new value will equal the old value minus f at old divided by f prime at old. Don't forget they gave us the first value, our first guess, x1. So if I want to find x2 using Newton's method, I'm going to take the old value of 1 minus, now I need to do f at 1. So that's going to be 1 squared minus 2, all right, that's f at 1, divided by f prime at 1. So that'll be 2 times 1 because here's f prime right here. So that's going to be 1 minus, well, that'll be 1 minus 2. So that's negative 1 over 2. So this is really going to be 1 plus 1/2. So that's going to be 3 over 2. So this is x2. So if I want to find x3, then I repeat this process, but now I'm going to do, my old value is now 3 over 2. So that's going to be 3 over 2 minus 3 over 2 squared minus 2 divided by 2 times 3 over 2. Remember, if you hit alpha, y equals, enter, it makes a nice fraction. That's how you should always make your fractions. So I'm just going to, I'm going to type in this entire thing, like 3 over 2 minus the rest of it. So in the calculator, it looks like this. I'm going to go ahead and hit enter, and I'm getting 17 over 12. So that is my x3 is 17 over 12. So if I want to find x4, I'm going to now start with 17 over 12. And now I will have 17 over 12 squared minus 2 divided by 2 times 17 over 12. Well, that turns out to be 577 over 408, which is approximately 1.414216. So that would be our approximation. Let's jump on down to example 2. Use Newton's method to approximate the zeros of f of x equals 2x to the third power plus x squared minus x plus 1. Continue the iterations until 2 successive approximations differ by less than 0.0001. In other words, we need to keep going until we have two guesses in a row that have the same 4 decimal places. This time, instead of giving us a x1 guess, they're giving us a graph. So looking at the graph, we can see there's only one 0 somewhere between -1 and -2. It's pretty close to -1. So let's just go ahead and guess. We'll let our x1 be -1.2. That seems like a good place to start. For Newton's method, we are going to need the first derivative. So using the power rule, we're going to get 6x squared plus 2x minus 1. And then the constant gives us nothing. So here's the first derivative. So we can find x2 by taking x1 and subtracting the original function at, you know what, I'm just going to put f at -1.2 over f prime at -1.2. So I'm going to be cheating and using a calculator a lot, but just understand that I'm evaluating the original function at -1.2 divided by the derivative at -1.2, and we're going to see what we get. Your teacher may require a little bit more work than I'm about to show, but if you are allowed to use a calculator, I suggest using a TI-30XS multi-view. This will be the most efficient thing. I'm going to use the table feature, and the way the function is set up, I'm just going to put in x to represent our old value, and then I'm going to go minus, and then so in the numerator is f of x. So I'm going to put my 2x to the third power plus x squared minus x plus 1. And then in the denominator, that's going to be f prime. So I'm going to have my 6x squared plus 2x minus 1. So this table feature will do all of the work. I'm going to leave this on Ask X mode instead of auto. So all you have to do is type in your first guess and it will tell you the next guess. So I'm going to type in my -1.2 and it's telling me that my next guess will be -1.235114. So now I can find the next guess, x3. But x3 is going to equal x2 minus f at x2 divided by f prime at x2. So I'm just writing x2 instead of writing -1.235114 because the calculator is going to do the work for me anyway. So all I have to do is, for my next guess, I'm going to type in the what the calculator told me to type. So I'm going to put -1.23511450. I'm just going to type it all in and hit enter. So now it's giving me -1.233754. So for the next guess, I'm just going to do the exact same thing. So for x4, I'm just going to do x3 minus f at x3 divided by f prime at x3. So the calculator is already set up to do this calculation. all I have to do is tell it to do it using x3, which is the negative 1.233754. So that's what I'll type. So I will do my negative 1.233754. So my new guess is negative 1.233751. Now remember when we said we would stop? When successive approximations differ by less than 0.0001. In other words, we can stop when we get two values in a row that have the same 4 decimal places. So that means we're done, and this is our final approximation. There are 2 ways that Newton's method can fail. For one thing, Newton's method involves dividing by f prime. You can't divide by 0, so if f prime equals 0 at any iteration, Newton's method will fail. If that happens, try just picking a different initial guess, and usually that will solve the problem. But another way that Newton's method can fail is if the values fail to converge. In other words, as we make guess after guess after guess, the values are supposed to get closer and closer to a certain number. And that's our estimate, our approximation for the 0. But sometimes the numbers do not get closer and closer to a specific value. They do not converge. For example 3, I'm just going to show you what that looks like. The function f of x equals x to the 1/3 power is not differentiable at x equals 0. Show that Newton's method fails to converge using the starting value x1 equals 0.1. So remember, for Newton's method, we need the first derivative. So using the power rule, the 1/3 will come to the front. Then we have to subtract 1, so that's going to leave us with negative 2/3 power. That's the same thing as having 1 over 3. And I'm just dropping the x to the negative 2/3 power down to the denominator, where it will become x to the positive 2/3 power. So this is another version of the derivative. Now I'm going to still use my calculator to do most of the work, but I want to show you one thing. Remember the part of Newton's method where we do f of x over f prime of x. So in this case, that would be x to the 1/3 power divided by 1 over 3x to the 2/3 power. So just remember, if I'm going to divide by a fraction, I'm going to wind up multiplying by the reciprocal. So this is going to be the same thing as x to the 1/3 power times 3x to the 2/3 power. So you're going to see me type this into my calculator, but all I did was I multiplied by the reciprocal of this. That's where this is coming from. Okay, so let's again use the table feature of our TI-30XS multiview. I'm going to clear out the old function. And Newton's method says you start with your guess. So I'm just going to put x for the guess, and then minus, and then you normally do f of x over f prime. But like I told you, I'm just going to wind up doing f of x times this because I'm multiplying by the reciprocal. So I'm going to do x to the 1/3 power. Okay, so x to the 1/3 power. All right, times 3x to the 2/3 power. And again, we will stick with the ask x way. So our first guess is supposed to be 0.1. So I'm just going to type in 0.1, and that gives me my next guess. So x1 is 0.1, but x2 is negative 0.2. Let's keep going. So now we will put in the negative 0.2, and our next value will be 0.4. So it is not looking too good so far as converging to a single value, but let's look at one more value. If I want to find x4, I need to do my calculations using x3. So remember that x3 is 0.4. So I'm going to use the calculator one more time and type in that 0.4. Can you predict what I'm about to get? Maybe now would be a good time to guess. Look at the pattern. We had 0.1. Ignore the negative sign for a second. I had 0.1, 0.2, 0.4. Can you guess what the magnitude of the next value is going to be? All right, I'm hoping that you're guessing 0.8. It seems like the absolute value of these is doubling each time. 0.1, 0.2, 0.4. I'm betting the next one is going to be 0.8. Now, what about the sign? It seems to be going positive, negative, positive, negative. So I'm betting that the next value is going to be negative 0.8. But let's find out. Oh, look at that, negative 0.8. So now that you see that pattern is happening, we could go on, and you could bet that x5 would be positive, because that's the next one. You could bet that x5 is going to be positive 1.6, and so on. So because we can see that the magnitude of successive values is getting bigger and bigger and bigger, there's no way that this will ever converge to a single value. This will just keep growing and growing and growing in absolute value. So again, because the magnitude or absolute value keeps getting bigger, the values will never converge on a number. Turns out there is a special condition for convergence. Newton's method will produce a convergence to a zero of f of x if the absolute value of f of x times f double prime of x divided by f prime of x squared is less than 1 on an open interval containing the 0. That's a pretty ugly expression. Let's look at an example. Use the condition for convergence to show that Newton's method will converge to a 0 of f of x equals x squared minus 2, which, by the way, this is the function from example 1. Here's a little graph. We can see that there's a 0 somewhere between 1 and 2. The condition for convergence involves f prime and f double prime. So let's go ahead and find those. F prime, using the power rule, will equal simply 2x. And then the second derivative, f double prime, is the derivative of this, which is just going to be 2. So now let's set up the condition for convergence. So we're going to do f of x, which is x squared minus 2, times f double prime. So that'll be times 2, divided by f prime squared. So that'll be divided by 2x squared. And we want to see if the absolute value of all of that is going to be less than 1 on this interval. So let's simplify this down. In the numerator, I'm just going to write 2 times x squared minus 2. In the denominator, I'm going to go ahead and square this and put 4x squared. Now the 2 will divide into the 4 twice. So on my next step, I'm going to have x squared minus 2 in the numerator. But the 2 cancels with the 4 and makes a 2. So I have this. Now I'm going to take this denominator and divide it separately under each term. So that's going to give me x squared divided by 2x squared minus 2 over 2x squared. So simplifying a little bit further, we're going to have 1/2 minus 1 over x squared. Remember, we're looking at the open interval from 1 to 2, and we're asking ourselves whether or not this expression is less than 1. So think about if you substituted 1 in for x. So that would be 1 over 1. So we have 1/2 minus 1. So that's negative 1/2, and so that absolute value is definitely less than 1. Imagine if we substituted 2. Then this would be 4, so we'd have 1/4. 1/2 minus 1/4 is 1/4. That's also less than 1. So on the open interval from 1 to 2, this expression is less than 1. So Newton's method converges. Finally, let's use the condition for convergence to show that Newton's method will not converge to a 0 of f of x equals x to the 1/3 power. So the condition for convergence relies on f prime and f double prime. So let's go ahead and calculate both of those. F prime, using the power rule, we will have 1/3 x to the negative 2/3 power. Had to subtract 1 from that. And f double prime, so if I take negative 2/3 and multiply that by 1/3, that's going to give me negative 2/9. And subtracting 1, all right, subtracting 3 over 3, that's going to be to the negative 5/3 power. Remember that the condition for convergence begins with the absolute value of f of x times f double prime of x divided by f prime squared. So let's go ahead and start setting that up. So you can see that I've put each function in its proper place. So all I have to do now is simplify and then see if it's less than 1 or not. In the numerator, I'm going to keep the negative 2/9, but I can multiply x to the 1/3 power times x to the negative 5/3 power by adding the exponents. 1/3 plus negative 5/3 will be negative 4/3. Meanwhile, in the denominator, I need to square 1/3, so that'll be 1/9. And then, if you square a variable and its exponent, all you do is multiply the exponent. So I'm going to have x to the negative 4/3 power. I'm just doing negative 2/3 times 2 is negative 4/3. So that's very interesting. I'm noticing that I have negative 4/3, well, x to the negative 4/3 power here, and I have another x to the negative 4/3 power here. So of course, those are just going to go ahead and cancel each other out. So I'll go ahead and show the next step, even though you can probably see where this is going. In the numerator, I have my negative 2/9. In the denominator, I have 1/9. When you divide with fractions, you multiply by the reciprocal. So I'm going to have the absolute value of negative 2/9 times 9, like 9 over 1, if you will. But you can probably see that these 9s are going to cancel each other out. So that's going to leave me with the absolute value of negative 2, which is equal to positive 2. Since this expression is not less than 1 for any x value, you cannot conclude that Newton's method will converge.